So I wanted to talk about interrupts. I've given you a Craig and Dave video link for that, but I wanted to do my own thing as well. So let's have a quick look at the specification, and it says you need to describe the role and operation of interrupts. And it says including how an interrupt is generated, how it is handled using an interrupt service routine, and what happens as a result of the interrupts. You need to know that interrupts can be generated either by software, for example, division by zero, or two processes trying to access the same memory location, or hardware interrupts, for example, pressing a key on the keyboard or moving the mouse. In reality, though, although those are the only ones that are listed, you do need to know or be familiar with other types of interrupts. For example, when a printer runs out of ink, it's going to send an interrupt to signal back to say that it's run out of ink. When it runs out of paper, when there's a paper jam, all of those are likely to send an interrupt. And so the first question then is, what is an interrupt? So before we talk about what an interrupt is, I'm going to talk about why we need them, or the benefits of an interrupt. So I'm going to go back prior to interrupts. So before we do that though, what I want to do is look at the key words and definitions. If you're aiming for a C, then this is the part that you need to pay most attention to. So an interrupt is a signal to the processor that something needs its attention. Now you can see here that there's a table with division by zero and two processes attempting to access the same memory location. Those are software, and those are in the specification. And under hardware, you've got data input, for example, a keyboard press or a mouse click, which is what was from the specification. But you also have these others, so error from the hardware, which is what we said, printer out of paper, printer jam, printer out of ink. There are a number of different things that need the computer's attention while the computer is trying to get on with what it wants to do. So what are the key features, things that you need to know? Well, interrupts are managed by something called an interrupt handler. And every interrupt has a priority level. And then interrupts are placed in the interrupt queue, so we need to remember there is something called a queue, and they're put there in priority according to the priority level. Then every interrupt itself has an interrupt service routine, and that's simply a program with a set of instructions that themselves need to be fetched, decoded and executed to do whatever needs to be done for that interrupt. Now, you need to be able to understand this process, and this is, if you want to get a C, you can remember this, read it, remember it, regurgitate, and you are likely to be getting a simple C. So we need to know that when an interrupt is generated, it's given a priority and placed into a queue. So remember, the interrupt could be generated by a key press or an overflow interrupt or many different things. When the processor has finished its current fetch, decode, execute cycle, it's then going to check the interrupt queue. Now, if the priority of that interrupt is higher than whatever task it's currently processing, it will first need to store whatever it's doing right now, all the contents of memory, for example, the CIR, the PC, the MDR, the MAR. It's going to need to put all of that into memory. Then it's going to go and fetch the actual interrupts. Once it knows the type of interrupts, it then is going to say, well, what is the interrupt service routine that I need to call? And it's going to call that ISR. When it has finished that interrupt service routine or that program, then assuming there is no higher interrupt, it's going to go back and retrieve that data it's stored and continue. Otherwise, it's going to repeat this process. Now, of course, when it checked the interrupt queue, if the interrupt was lower than the current task it was processing, it will just simply go back and keep running until there is a task in the interrupt queue with a higher priority. Now, as I said, if you're aiming for a C, that is all you need in order to read, remember, regurgitate. So The next part of this video is to go through more of the detail, and so that you can understand it, and hopefully if you're understanding, if you come up with a more application style question, you will be able to answer that question as well. So I said earlier that we want to talk about life before interrupts. So I want you to imagine you're sat in your bedroom watching the television and you're waiting for a parcel, and that parcel delivery driver is lazy. He's just going to leave it on the doorstep and then go. Now, you don't live in a bad neighbourhood, so it doesn't matter if it's left out there for a little bit, but clearly you don't want to leave it out all the time. And of course you're waiting for it, so you don't want to leave it out there forever. So what you need to do is you're in the middle of watching television, and then maybe 5 minutes later, you're going to go outside, you're going to say, oh, it's not here. So you go back to watching the television. Then maybe 5 minutes gone again, you go back and you check and you say, oh, it's not there. So you go back to watching the television. Then while you're watching the television, the delivery driver comes along, puts the parcel on the step and leaves. And then next time, after 5 minutes has elapsed, you go, there is your parcel. Now, once you have your parcel, you're going to want to do something with it. Let's call it the parcel unwrapping procedure or subroutine. And then when you finish with that, you're then going to go back and watch the telly, and of course you don't need to go and check outside anymore. That process is called polling, because we have to set a timer and then we have to keep going out and checking every time. And it's inefficient. It'd be much nicer if, let's say for example, we could put a pressure mat on the doorstep, so when the delivery driver put it on the doorstep, it would send a signal, perhaps ring the doorbell automatically for you. So now you could just carry on watching the television until the doorbell interrupts you. At that point, you know there is something that you need to do because you've been interrupted, and therefore at that time you will then go out and collect your parcel. So that is what an interrupt is. Essentially, it allows you to carry on doing whatever task you're doing until a signal tells you you need to go and do a different task. Let's look at this in another real world example. You're in the emergency room and we have a patient queue. Right now there's nobody in the queue. We have our admissions nurse and we have some doctors who are currently discussing the needs of a particular patient. And along comes Bill. Bill has got a cold. Well, at the moment, nobody is in the queue, so Bill will go to the front of the queue and the admissions nurse will send a signal, an alarm, go over and tell the doctors and her nurse that there's somebody in the queue. They will then check the queue and they'll see it's Bill with just a cold, and it's not really as important as the needs of the patient they're looking after. So they say, I'm going to carry on with this task. Then along comes Jill and she's got a broken arm. Well, clearly a broken arm is a much higher priority than Bill's cold. So the admissions nurse puts her to the front of the queue and again sends a signal to the doctor and her nurse. And they then, when they finished their sentence, they then check the queue and they go, oh, a broken arm. That's definitely more important than what we're doing with right now. And they know that if there's a suspected broken arm, the protocol says that you x-ray it. So they need to carry out a specific routine. We'll call it the x-ray routine. So Jill is going to get x-rayed. So she's in the middle of a task that the doctors are performing. And of course, Bill can now come to the front of the queue because he's the only person left. Now let's say we've just taken an x-ray of Jill and she's lying there quite comfortably. The x-ray machine is off and they're still in the middle of attending to Jill. But along comes Jack. And Jack has got a head injury. So clearly a head injury is more important than the cold. So the admission nurse puts Jack to the front of the queue and then signals to the doctors and say, hey, we've got something for you again. So while Jill is laid down comfortably, the x-ray machine has now been switched off, they check and they go, oh my goodness, a head injury, that's even more important than what we're looking at right now. So we need to follow the head injury routine, which is to go into theatre. So they pause what they're doing with Jill, she's in a stable state, and they go off and deal with Jack. And they're now following the operating room subroutine or service routine. When they finished with Jack, then of course they need to go back and finish off with Jill. And then finally, when they finish with Jill, they then check the queue. They say, oh, we better deal with Bill. They deal with Bill, and that is the end of the process. So let's go back to what we looked at before. So we said that interrupts are managed by an interrupt handler. So in that case, that was the admissions nurse. All interrupts have a priority level. So for example, a head injury is a higher priority than a broken arm, which is a higher priority than a cold. So we saw that interrupts are placed in the interrupt queue in a priority by the interrupt handler. And then every interrupt type has an interrupt service routine, which we've said before. So in this example, there was an X-ray interrupt service routine, and there was an operating or head injury interrupt service routine. So what we need to do is we need to extend our understanding of the fetch, decode, execute model. So what we actually need is, after we finish the execute, we need to do a further task, and that is to check the interrupt queue. So let's look at an example. We can fetch, we decode, we execute, and then we check the interrupt queue. Now in this queue, we have a printer with a priority 1. That's a low priority. It's lower than what's in the queue. Sorry, what's the currently running tasks. So we go back and we fetch, decode, we execute, and while that is running, another interrupt comes. So we check the interrupt queue, and we see that we have a overflow, priority 5. That's a high priority level. So we need to deal with that. So what do? Well, we need to again think about the central processing units. We should know this is a familiar diagram. So right now you can see, although it says program counter is 3, that always increments before we carry out the previous one. So we're just finishing the execute part of the operation at address 2. So we've done our fetch, we've done our decode, and we've done our execute. We know that there is an interrupt. So the first thing we're going to need to do is we're going to need to store all of the information that is in here, 3, PC in here, 101, all of these, all of that information gets stored into a special structure. We call it a stack, but in reality, this data is actually part of this main data, but I'm drawing it separately so you can understand it. So we then say, well, what type of interrupt was it? Well, it was an overflow interrupt. And we can see here that the program or the procedure or the instructions for the overflow interrupt service routine start at address 1000. So what we need to do is we need to put address 1000 into the program counter. So now the instructions are going to start here, and it's going to do the code for the overflow, whatever that is. And when that is finished, what we'll need to do is we'll need to then load all the data back that we originally had and remove it from memory and put it back into the immediate access store, the program counter, the current. And so we're now ready to start the existing task that was there. And so that is how the interrupts work in reality. So we need to summarize and go back to what you might call the read, remember, regurgitate of how what we've just said works in practice. So what we said is that when an interrupt is generated, it's given a priority and placed into a queue according to its priority. When the processor finishes its current fetch, decode, execute cycle, it checks the interrupt queue, and if the priority of the interrupt is higher than its current task, it will store the current task in memory. We saw that, how we took the CIR and the program counter and put it in that special memory place. Then it fetches the interrupt. It says it's an overflow. So it checks it as an overflow, and it says, how does it call the relevant interrupt service routine? Well, in reality, it says what is the starting address of that and loads that into the program counter. So it calls the relevant interrupt service routine. And then when it's finished, of course, if there's another even higher priority, then it's going to fetch that. Otherwise, it's going to retrieve the original stored task, which is what we saw the data going back into the immediate access store. And of course, originally when it checked the interrupt, if it was a lower priority, then it's just going to keep going, which is what we said before. So hopefully, if you go through that video a few times, if you remember the read, remember, regurgitate at the beginning and this final summary, you will be as an easy C. If you can get your head around how the actual interrupts work, then you are headed for a B or an A if you get a more application style question.